I just told everyone I'd introduce myself because you're all like used to me by now, and I didn't think to ask somebody to do it. So I was in Ohio at Case Western Reserve University, which I'm looking for Lisa. Aha. We have a Case Western Reserve alumni or a student here. So that's where I went to school, and one of the best things that I got from there, besides a great education, is my husband, who followed me to Boston. No, we just both were able to go to Boston and get our PhDs at MIT. And then I did a postdoc at the Air Force, so it was a National Research Council postdoc, which was a great opportunity to see some national lab as well as academia. And then we moved here. He works at Medtronic on pacemakers, if you're interested in pacemakers, which there's a lot of magnetics and biomedical applications now. And I was able to join this department, electrical and computer engineering. I also do a fair amount with the Materials Research Society, so if any of you are interested in that society, you can talk to me. But this particular talk is for the IEEE, so I feel like I shouldn't say too much about the MRS. But I served on their board of directors and was secretary for 3 years. And other than that, you can look my bio up online. So my distinguished lecture talk for the year 2015 is on magnetic nanowires. I'm probably just going to point at that one, but this is so you can focus in better. I have photos of the students whose work is actually in this presentation, but in red I have my current students and then other students who have worked with me over the years, undergrads and grad students, top line, undergrads in the second line, and then a bunch of collaborators. And this kind of comes to that question that we talked about in the last discussion, that I haven't learned a lot about bio except what I can pick up from reading some textbooks, which is different than really having a degree in bio. But I do work with a lot of collaborators who know a lot more about bio than I do. NIST does some neutron scattering with my nanowires, and University of Maryland, Allison Flaytown, I have funding together for like 15 years or something doing sensors. And the rest are all medical collaborators because they actually have sterile labs where cells live. I don't think they'd live. We had cell culture in my lab, but not actually living cells. So I'm glad to work with those people. So magnetic nanowires start with an oxide template. These are empty oxides. And so I kind of have white letters because they're empty. And when you fill the templates, just like the letters are filled there, what you're left with are wires. And if you etch the template away like there, you can see what the wires look like. And we use them for, sorry, like the title says, hard drive actually reads sensors more than anything. Random access memory is kind of something we've looked into, keep sort of looking into it further, but I don't have a lot of results on that. And as I mentioned in the discussion last time, we've been doing a fair amount on cancer therapy. I don't have our latest results in here, partly for reasons Professor Cowborn mentioned. We have some pretty good results. I'm hoping to see if we could move them further ahead and actually apply them to therapy at some point. But I'll show you what we've done along the way just to prove toxicity, that they're not cytotoxic. All right, here's the IEEE magnetics.org advertisement, which should come with every DL talk, but you know well about it, especially because I tell most people I speak to that they can look for our conferences and attend if they're interested, and also that there's a summer school that is this year in Minnesota, and you all know that really well. So now I think I have to take that off or say, well, this is what happened this past summer. And you've been on that boat, so this is the only audience I'll be talking to where everyone's like, I know that boat. All right, so here's a hard drive. Some people talk about maybe media because the tops of the wires are all very uniform. Maybe could be media. I'm more interested in this idea that we could have some nanowire that would act as a read sensor. And actually, Randy Victor and I developed this idea for some funding a while ago, and we're sort of looking for companies that might be interested because in particular, we grow them in arrays. I should say my group grows them in arrays, and we have theory because we talked a lot in the last discussion about coupling with theory and experiment, and that's what we've been able to do on read sensors. So here, there's a little array. It's very handy if you want to try and get higher and higher density. As you head towards a bit error rate that's like, 10 to the minus 3, meaning instead of 1 in a million or 1 in a billion, you're talking about 1 in 1,000 bits being wrong. You still want to get your data back. It would be nice if you could read 3 tracks in a row, subtract the adjacent tracks from the one you're trying to read, and you could do more accurate reading. And then we have RAM, the idea that maybe initially a couple of wires could be a bit, but as the lithography scales, it's not something I really want to work on myself because it's the active layers that I'm interested in. Then our active layer is already the right size. So instead of scaling, normally the active layer is a hard thing to scale. So I draw it like that just to show the idea that even soon it could be useful for storing a bit. And reading out, getting a transistor involved and everything else is, of course, going to be more complicated. But I want to show you the active elements and the physics of that and see where it could go. We also use them for cilia sensors. They're a million. They're basically like a 4-inch piece of hair that's shrunk a million times. So here, what you see is an AFM probe. So that's a tip of an AFM with a cantilever that goes way out here. So normally you think of an AFM probe as being very small, but that's our nanowire adhered to it, and it's just wiggling as we're trying to measure the Young's modulus. And finally, the cancer therapy is more the idea that cells like to internalize these nanowires. And if the cells want to internalize the nanowires, and the nanowires carry with them a barcode and a magnetic piece, which could be used in hypothermia and also in some new therapy that I'll show you later, that's where we'd like to use them. All right, so that's kind of the overview, so you can kind of hang everything you're hearing on that outline. You have already learned a lot about this, but I share this with some audiences that are students that might not already know anything about magnetism. And of course, you know that a magnetic hysteresis is going to pick up the entire sample, all the magnetic moment as it points in the direction that you're measuring it. Whereas magnetoresistance and spin transfer torque switching, you're actually just, if this is a nanowire, you're applying a voltage from the top to the bottom and therefore running a current through it. So you're measuring more directionality along the wires as opposed to the entire sample and everything going on all at once. And so just what do those two things look like? Well, again, you've already seen VSM several times, but I just want to mention there's a field in this direction because these copper windings apply a field with the right-hand rule that we've talked about. But our VSM, maybe I will actually point in the middle here, it has a special feature where there's this extra Teflon, there's coils inside the Teflon here as well as here. So even though we're always applying a field in what we'll call the X direction, which would be like this or like that, we're able to pick up a magnetization perpendicular to that also. So if we see a coherent rotation as the reversal mechanism, we'll see a moment perpendicular to the applied field. And just to show, you've seen several of these also, shape anisotropy, imagine a nanowire. They can be 10,000 times longer than they are in diameter because the way we grow them, it's not a lithography process. So we can end up with pretty high shape anisotropies. Here you're seeing, depending which way you apply the field, parallel to the wire or perpendicular, you can have different shapes to the hysteresis loops. And those two aren't corrected for anything, so there's a little variation where you might not expect it, but I just want to show you the loops. Magnetoresistance and spin transfer torque switching, we're going to apply a current. This could be, for example, a gold-coated AFM tip. So you come down with a really sharp tip and try to just hit the top of one nanowire. And if it's 10 nanometers in diameter, separated from another one by 10 nanometers, it's pretty hard to find a tip that's as sharp as the schematic draws it. So what happens is you might come down with your tip, and as you put a little pressure on it, you pick up 2 or 3, depending on the rounding. And then you'll have jumps in your resistivity, literally because you're just picking up another wire, and you'll have parallel resistors. But meanwhile, you're sensitive to the direction along the wire. So one example of that is if we look at the resistance versus applied field, this is an entire array of nanowires. And if I want to put it in my VSM and apply a field perpendicular, then take away that field and apply it perpendicular, take it away and go negative to positive, perpendicular to the wires, I'll measure a certain resistance change. And if I take and orient the wires so they're parallel to the field as I apply it and take it away, I'll see another resistance change. And what happens? Well, if I have the C-axis, cobalt, you'll remember from the other talks, has a very high crystallographic anisotropy. But I'm going to grow a pancake shape. So the shape anisotropy is going to be a pancake, and my crystalline anisotropy, in this case, is along the pancake. And what you can find is that the resistance, well, up here it's pretty high because the layers all go back to being antiferromagnetic. Then I apply a field, and they're aligned, so the resistance drops. Then I take the field away, they're antiferromagnetically coupled again, so the resistance goes up. Then I go the other way, and so on. So I get an increase in the resistance when I'm at 0 because they're antiferromagnetic there. I don't know a lot about them, but I can see now the VSM loop of these actually looks the same because I'm measuring all of the layers in every single wire in the sample when I use a VSM, where here I'm measuring properties that are specific to along the wire. So what happens if I change the anisotropy? So here I have a c-axis that's perpendicular to the shape. The shape is still a pancake, but the c-axis is perpendicular to that. And now what you find is if you orient the same way, go ahead and have all your wires lined up and apply the field, take it away, apply the field backward, forward, you still get the very similar shape to the curve. But if I go and tilt my wires this way and magnetize them parallel, well, one of the easy axes is actually along that axis now. And there's a little more to it because also if the spacing here is different, that's going to also favor an anisotropy along the wire. But basically, you can see the difference in the magnetoresistance because you're sensitive to the current along the wire. And if we're making domains by magnetizing it parallel, and those domains, well, you have a closed loop here, so they're happy to stay. You have less scattering at those interfaces, so we don't have as high a resistance at the remnant state because we don't go fully back to antiferromagnetic. All right, also small angle neutron scattering is very unique in that we can hit the entire sample of nanowires with neutrons. They are going to be sensitive to the magnetic moment, and it's very hard, really, even with the magnetoresistance, to even measure one wire. We've done it at times, but it's difficult. But to actually try to say what's going on inside that array all at once, it's opaque. You can't bring in a magnetic probe inside that. They're all very small. But neutrons, it turns out, if there's any kind of coherence, they'll diffract off of that. So here you can see this is the samples now are in this direction, and the neutrons are coming at them and then scattering onto the detectors that you're seeing here. So the scattering in this direction is from the interwire diffraction, basically, scattering. And if you can go in this direction, you actually get, is there any layer to layer? Because your nanowires have layers, pancakes inside of them. And this is something I just want to point out. The paper's coming along. Our NIST collaborators are working on that. But it turns out the idea, let's say that I have a nanowire with pancakes, which is, this is one nanowire represented right here, and my fingers are the pancakes of cobalt. If you magnetize it that way, we've thought when you go back to zero field, they're antiferromagnetic. You magnetize it that way, they're all ferromagnetic again, and so on. But it turns out in this state, what we're seeing with the neutrons is instead the pancakes do all, if you apply a strong enough field, all the cobalt follows the shape anisotropy, plus basically they're just magnetized by the field. But when you come back to zero field, there's actually domains of pancakes that stay magnetized together, and that forms an isotropic shape, which seems to make sense for some energetics also. And we're working through what that actually looks like, and it appears to be a bit of a spiral. So there should be some very interesting results coming out soon that we really couldn't see any other way because all those spirals are coupled to each other. So it's only the magnetic moment in the entire sample that ends up giving you this particular state. So neutrons, hopefully we'll have that soon. So now you might be asking, we really haven't heard much about electrochemical synthesis this entire week. This is a field that really favors vacuum deposition. Did anyone see the electrochemical deposition at Seagate? All right, one took note. I know for my group, we all went different directions, but for my group, it was around the last corner. So we were in a bit of a race at that point, realizing that the buses were already outside the building. We had to leave, but there was a huge section. They actually have a lot of coders, not like just one that they do a little bit, but the shields and the right poles, they're all done with electrochemistry. And I kind of double-checked that again last night so they could kind of hopefully not give anything away, but say they do have a lot of electrochemistry going on. But it's not often in the active elements, like the read element. It's in the right element, which is active, but not in these layers. And we even asked our guide at one point, what is really the most critical step in this fabrication? He said the reader layers, the reader stack. So they're sensitive to the idea of using a brand new technique to replace this kind of highly sensitive part, but they already use this technique in many ways, and we're trying to show them you can use it as controlled as you could do vacuum chemistry. So why would we want to do electrochemical synthesis? Well, what we're seeing now with the read layers is that you do this lithography. Everyone draws layers like this to say we're going to have a synthetic antiferromagnet and then a ferromagnet and then a spacer and then another ferromagnet and so on. You build up this sort of schematic. Then we'll put a blob of photoresist, pattern away everything but what's under the photoresist, and that's your device. But what really happens, and I used to have a figure there. I took it out. There's sidewall damage here. Because you're basically, when you're ion milling, you're atomic sandblasting your sample. And that means you're going to have some damage at the side. And the smaller you want to make that circle that's being etched away right here, the more the sample is side. So if you've damaged it, you have a damaged sample in the end. What about thin film growth by itself? This is sort of representing evaporation, either thermal or E-beam, but sputtering as well. What you really get when you have vapor deposition is something that's called the Thornton diagram. So depending on what pressure you apply at and substrate temperature, you can get any one of these microstructures. But often they stay down in this, they don't heat the substrate for a lot of the growth, or as you pattern away, as the smaller you want to make that bit, do you have a grain boundary or not in your device is going to change its properties. So if all of your read heads on that wafer they're making at once, if they don't all behave the same way, then it's hard to really calibrate and make sure that your bit error rate stays low and you can take advantage of the high areal density. So this is one reason why you might not be as interested in doing sputtering. And then the idea of even just sputtering away these layers, if you want to try to have two next to each other, you might find that you're coating the sidewalls. Because you sputter an ion off this spot and it hits the sidewall of the device you want to keep, now you've coated the sidewalls by resputtering. And the last thing people sometimes say is, what about liftoff? Because if you do liftoff, then you would have your photoresist down, put your layers on top, and when you lift off the photoresist, now you're left with nice pristine layers. And there are tricks that were even pictured around the Seagate walls, I took note, where you can do kind of a two-step photoresist and so on. But in one case that we had, we patterned nanostructures and we put down films, and it doesn't look like this at all. And that means that your sidewall, if you're relying on this pristine layering, but you want a diameter that's really small, what you might find you actually have in your device looks more like that. And that's going to behave differently than this behaves. So it's just something to be aware of and think, is there a way I could overcome that? And even if you have like a hole and a two-step resist, you might just end up with this bottom blob, even if you end up not having sidewalls. So maybe it still ends up being structure you can use, and then that's fine. But the smaller you make it, the more you have to ask yourself that question. All right, so if instead we have a template that has holes in it, and we start at the bottom, instead of having atoms come from the top, but we actually charge this and attract ions, now they deposit on the bottom from a solution and build up the pores. And then you can end up getting a nanowire that looks something like this. Now, these layers are very, the interfaces are good, but you can see there's sidewall damage because this had to be removed from the oxide in order to image it. And that removal process is corrosive, so the wire gets corroded. And that's X-ray map, so you can see the compositions there. And we'll go through different wires where they're still in the oxide, so they're not damaged, and then they have very smooth sidewalls. So it's always challenging to try to get a zoom up of the sidewalls. I think if you look on the sides, it's a little better, but they really are very smooth aluminum oxide, and then the metal grows inside there. It has a conformal coating, so you end up getting sidewalls that mimic what you see in the oxide. All right, can I just ask how many people here do anodic aluminum oxide? We haven't had much in the lectures so far. I know Russell's going to mention a collaboration. Anyone else here? One hand? One very shy hand, too. Okay, very quiet hands go up. Are you embarrassed about it or something? It's so nice I can tease with you now, an audience I know better than most. All right, well, why anodic aluminum oxide? So just in case you haven't heard before, what we're going to do is take aluminum and make it the anode of an electrochemical cell. So whenever you hear anodic aluminum oxide, it's because it's an anode when you make it. So you start with aluminum, but just remember, because I still, even after saying this sometimes, I have people say, why would you be able to electroplate when you've got a matrix of aluminum with holes in it? But this is not aluminum, it's an oxide. So we start with aluminum, and as the oxide grows, it has nanopores in it. We need a counter electrode. Depending on the voltage, the electrolyte, and the temperature, you can get a range of different pores out of this. And they self-assemble naturally. But if you're buying them commercially, you might end up getting something that looks more like this. So just be careful, because if you're buying just a filter, like a Wattman filter, they're not designed to be templates for nanowires. And you might find that you're not really getting a nanowire at all when you grow in these materials. But if you make your own, or there's some companies that are getting better at selling higher quality templates, you can see all of these have the same diameter anyway, even if they're not in a perfect line for a very long range. So if you were to follow one row of pores, you see that it goes off to a distance. So it's almost like grain boundaries. But the sidewalls are very smooth for the entire growth. If you zoom up, you can see they're very uniform. So how do you do those? Well, here's my aluminum, and I'm oxidizing. And from the beginning, the oxide looks pretty bad. Just finds a minimum in the substrate, starts to form a pore. As it's oxidizing, these pores grow. But the further you grow this oxide, the ordering is actually happening at the aluminum oxide-aluminum interface. And as that interface is ordering, it means that the longer you grow that oxide, the more ordered these dimples basically become in the aluminum. When you etch that oxide away, then you have aluminum that actually looks like this. So that's the metal now. And what happens here? Well, how long does that take? Well, you know, the more time you have, the thicker the aluminum film that you have, or even a piece of aluminum foil, the more ordered your pores could be. But after really like even just minutes, they're not bad. Often there's papers that talk about 16 hours. If you're starting with an aluminum foil and you've got a bunch of grain boundaries, so a really rough surface, then longer is better. If you're starting with a film that you've deposited on silicon, it's fairly smooth, so you can go not so long and get pretty good quality. But in the case of a foil, which this was representing, you've worked 16 hours, then you etch the whole thing away. It's a bit of a bummer. But then when you start with this aluminum under the exact same voltage, temperature, electrolyte, all the pores have a place to start, and they just grow from there on. So that's when you end up getting very smooth sidewalls. So we said to ourselves, and unfortunately, a few other people said this to themselves before us, what if we dimple the aluminum ourselves? Now, instead of waiting on nature to self-assemble some pores, we're going to tell the pores where to start. So we made a nitride stamp, imprinted the aluminum, which is soft. You can make a lot of dimples on the same piece of aluminum, or on multiple pieces of aluminum. If you oxidize that, this kind of just an AFM, you have to come in maybe 20 nanometers. Then it turns out that your pores form right where you had the dimples. So you really can steer where you want them, yeah.
How do you make the stamp? You have to have a mold or something to stamp
Yeah,
it?
so we use e-beam lithography for that. So actually it's a very good question because this is my next point, is that initial stamp costs a lot of money. And let me just show you what the pores look like up close, and we'll talk about that. Okay, there's the sidewalls, and that's the other, the straight sidewalls. All right, so this stamp was 1 millimeter by 1 millimeter. And back maybe 10 years ago, it cost something like $1,000. All right, so maybe only 4 years ago, we got a brand new e-beam lithography tool here at the University of Minnesota. And I asked the technician that was being hired with the tool, so he knows how to use this thing, he's ready to go, how long would it take to do a 2 by 2 inch square? So that's 5 by 5 centimeters, since we're such an international audience here. And he said, well, you know, probably a long weekend, writing all weekend, which we could do for you if you want, be about $5,000. You know, that's a remarkable new tool. You know, it does a lot more area, all perfectly lined up, so that would be great. Let's sign up and do that. I'll raise $5,000, no problem. Have a nice big stamp. They'll all be perfectly ordered. And then as they got doing dose testing and checking it, he came back and said, you know, there's this factor that's normally negligible that for you is kind of multiplied by 1 billion. So it's going to take 23 years of constant writing. I said, okay, I think I can do that. And he's like, forget it. You can't do that in my machine. So, yeah, there's no way we're going to do 2 inches squared on an e-beam lithography tool. Now, we've also gotten smarter that, as you were maybe already thinking, we now do an e-beam lithography in silicon, and we grow nickel on top of that. And we are good at electroplating now, so we can pop that off and use that as our stamp. So we can spend a lot on that on the master, make a lot of stamps, use each of those stamps lots of times, like 100 times. We can get a lot of samples out of one master. So to spend some money is fine, but 23 years is probably not going to happen, right? So instead, what we ended up doing is writing lines. Yeah?
How many times can you use the stamp?
Each stamp, we have used them like 20 or so times, and we kind of end up switching to a new parameter at that point. We anticipate we could use each stamp 100 times. I should also mention it depends a lot on how you're pressing. So if you use a nano imprinter that has a regulated printing, which there are a lot of these in industry, and also Seagate does have, they have made 20 nanometer dimples over an entire, I think it was a 4-inch wafer. So you can do it by different lithography means than we have available. And the imprinting, if you're very careful, let me just show you the motion we use when we nano imprint, and you might understand why we only get 20. It's a pneumatic, psh, 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 right? And then we stamp, right? If we had sort of this as our motion, then we could get 100 stamps out of it because we'd have a controlled process. And you can see the automation that Seagate can do. So if they're at the point of being interested in it, they could go ahead and make a lot more imprints than we can make. All right, so now we're doing lines instead. It turns out with lines, what they had told me is the more you could space those things apart, so the fewer times you're actually writing dot, 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 then it's really exponentially faster to write it. I'm like, what if we just go, shh, shh, that would be, even quicker. And he said, yeah, we could do lines. Sure enough, long weekend, $5,000. So instead, we opted more for 1,000 again and using kind of a long deposition. And here what you see is just a 1 centimeter. So that blue is 1 centimeter in diameter. And the only reason it's blue is because we took our sample like this and we look at it until we see a diffraction of the light. And the spacing gives us blue. And as we rotate our sample, we see that blue flash 6 times because it's hexagonal. But otherwise, it's gray, like the outside of the blue, because they're just nanowires. So we know they are perfectly ordered, or we wouldn't see blue. And that's a centimeter in diameter, which means 3 billion nanopores all lined up perfectly. And this is the side of that one, because if you grow on silicon, or if you just grow a thinner layer and bend the aluminum to look at it, it won't be as thick a pore. I know people who make and sell 100 micron pores, so it's possible to go 100 micron with a 10 nanometer diameter. So I've seen 10,000 aspect ratio for a pore, and I just don't know anyone who wants higher than that. I think it could go on for quite a while, but by that point everyone says, great, give me the pore, give me the wire, and that's all they need. Okay, so that's the pores, yeah.
So you said you're drawing the lines, and instead of drawing each pore, each hole, in this case, they're not going to be round, right?
No, it'll just be a line,
so
yeah.
You're not going to have nanowires, you're going to have like parapipedic shapes?
You have to stamp twice. Stamp, turn 60 degrees, stamp again.
Oh.
Yeah. And then you end up with a low energy spot between those.
Okay.
Are you sure you don't do electrochemistry? Okay. Anyway, we'll fill the wires. So what do they look like when we fill the pores? Well, first is if you're growing on aluminum foil, then you need to get rid of the extra foil you're not using. If you have this sample on silicon and you've deposited copper and then aluminum and anodized, so you use the copper to anodize the aluminum. When you run out of aluminum, you've got pores on copper. Or if you grow on foil and you have to get rid of it and then put some kind of electrode, we've used the normal electrodes, copper, titanium, copper, chromium gold, tungsten gold at times, just different contact materials down here. Now what you want to do is encase that entire thing in polymer. Now I had a student, since you're all students, I can tell you this. I don't always share this story because it's a little weird, but he tried every polymer he could find and everything that he could then dip into this bath. You need the back to be protected from the electrolyte, or you're just going to grow a film on your copper there, right? So he was protecting it, dipping it in, trying to make sure that the only place the electrolyte saw contact was down inside the pore. Then you're going to deposit metals as you build up a nanowire. Finally, you know what the polymer he found was? Nail polish. Excellent. I'm one of 2 women in the entire department. Now all my students go and get their favorite color. Right away, that's my sample, it's green. They can all identify all their samples. So we sometimes call it polyacrylamide or something because that's also nail polish. But it's a great cover. And then you can dip into the electrolyte and not worry about having the backside coat because that swamps the entire procedure then. All right, then in this case now we need a reference electrode, which is this kind of bubble thing here, because you really need to know exactly what is the potential at your surface because you're relying on the reduction potential and how much below that you are when you're depositing. And we still need the counter electrode and so on. All right, so that's what they look like. And if you want, you can block off nanowires using the edge of an imprint. The one I showed you wasn't so sharp, but this one was a very sharp one. So we lined photoresist with an optical microscope. You can't see nanostructures, but you line up the edge with the optical microscope. That lines up your lines of photoresist, and you end up growing rows of wires, which is very convenient for a lot of applications like MRAM and maybe even hard drive heads and so on. And you can even see back here there's a crack, because this is the growth electrode. We didn't take the wires off the growth electrode when we etched the oxide away, which is why there's still kind of some junk up here too. We just wanted to see what that would look like. But we can also completely free the nanowires, and then they look like this. This is actually, they're also still on the growth contact. It's kind of down here. So they're kind of spread out like a bed of seaweed. And we can take them out of solution. Here they're still in the oxide. We just bent it and we're looking at the side. So they're all lined up. So these blue layers are lots of nanowires going this way just to check their uniformity. And we grow copper, gold, copper, cobalt, nickel, iron, gallium, which is a magnetorestrictive alloy, so it's very handy. And we call these sometimes nano-barcodes because we can grow so many different kinds, a lot of different properties. So I said in my abstract I'd give some synthesis secrets. Anybody wants to try this. The first thing you want to do is called cyclic voltammetry. Apply a range of voltages and measure the current. Sometimes you see this curve flipped upside down. There's a lot of kind of sign confusion, I think, depending on who's reporting it. You'll find papers that are more material science engineering that have it this way. You'll find chemists or electrochemists that like to plot it upside down. But the general idea is if you're not getting much current, you're not depositing or etching anything. And here we're depositing copper. We start depositing cobalt here. And then you etch the material if you're at a different voltage. So you just need to kind of be aware of what's happening in the solution as you go. And so here's the trick of growing multi-layers. Fine if you just want 3 like a reed sensor. Just put it in one electrolyte, switch to another electrolyte, switch back to the first one. But if you want to build up 300 layers, so you make good like RAM type devices or these barcode devices, it'd be nice to have all those layers grow at one solution. Leave it in there and just change the voltage. So in this case, what you want to do is put in 100 times less noble metal than you have of the other metal. Right? So in our case, it's copper, cobalt. Copper is more noble. And that means it's going to deposit at a lower reference reduction potential. So somewhere around a half is the reduction potential. We're going to go a little below that because the over potential is what starts to give the copper 2 electrons, so it becomes copper. And at somewhere after 1, actually, that's not quite right because you can see where, oh, I see, right, voltage. So this is at 1. So the reduction potential of cobalt was a little less than 1. When we go to 1, we're only going to get cobalt. But that's not true, right? Because cobalt, 1 is actually, -1 is less than -5. So we will get copper at -1, and we're way below its reduction potential. So we have the potential to get, literally, a lot of copper in our cobalt. But if you have 100 times less copper in your pores, when you jump up here to 1 volt to deposit cobalt, it's actually diffusion limited. You get a little bit of copper in your cobalt, and then there's not any more copper ions in your nanopore, so you don't get too much copper there because there's not much in the bath. Then you come down below the reduction potential of both to kind of flush out the pore and pull back in solution, and you deposit just the copper. Now you have to sit here longer because you have less of it in the solution, and you have to overcome that diffusion limitation, which was why we had the flat line on the previous curve. The point is you really have to learn your bath and then design out how you want to grow these, and then you can get very uniform layers, except for a couple alloys, right? This one's not very uniform. This is actually iron gallium. And here you can see there's a whole lot of short ones and these weird long ones. And this is a hysteresis of it, a whole lot of short ones and some weird long ones. Not at all what we want. If we're going to try and make a certain property and we want all the sample to have the same property, that's not going to do. Well, iron gallium has particular problems. Gallium likes to oxidize. It precipitates out of the bath. It lands as a white powder in the bottom of your beaker, and therefore it's not in your wires anymore. So we had to learn a lot of tricks to get this particular alloy to form. And I never want to imply that like they're all impossible. Iron, cobalt, copper, a lot of your standard magnetic materials and just metals are pretty easy to deposit. But as a little sign to show we can pretty much deposit anything that can be deposited as a film, we can make it as a nanowire with tricks like this. So the first thing we had to do, which isn't on here, is find a complexing agent. And we have a paper on that. I should have put it here. But basically, you can keep the gallium in solution if you put citrate with it, so it stays dissolved. And then you want to use a rotating disc electrode. So you actually spin the sample itself instead of having a stir bar in the middle of the beaker or at the bottom of the beaker. You bring the solution up and have it rinse past the pores, so you keep a homogeneous diffusion layer outside the pores. And then you get a Gaussian distribution at least, but it's 27% relative standard deviation, not so great. So then we will go back to a trick we use almost all the time. Just put a little copper down first to make sure there's good contact between the contact film and the pores themselves. And then we get 7% standard deviation. And if you couple that with pulsing, which if you're doing layers, you're kind of pulsing anyway. But even if you're just doing a straight alloy, if you pulse it, you kind of rinse the pore out and bring in new solution a lot. And then we find 3%. I wish I had thrown in a blown out of this also, because it's just perfect for the whole thing. They're all really exactly the same length. Okay, 3%, not the same length. Pretty good. And why does it matter? Well, if I want to claim that I have different magnetic properties with this sample versus this sample, then I need to have grown the entire sample that way. Because otherwise I'm measuring an agglomerate of all of these in one hysteresis loop, and I can't really tell. Every single sample looks sort of the same, and that looks like a washed out version of all of these together. But once you control the growth, you can see that A here is very different from E. This is the coercivity versus angle. So basically, if my field is being applied this way, and then that way, and then left and right, and so on, if my wires are aligned at 0 degree as I'm applying the magnetic field, sweeping the field, or if I rotate this to 90 or to 180, then I'm measuring a different coercivity at all those angles. And that tells you a lot about the switching mechanism of the wires. And we have worked out why that happens. You basically, in this case, when you get this is like coherent rotation here, right? You have a minimum at 0 and 180, and you have a maximum at 90. You kind of expect that with if the moments are just rotating around. You'd expect that when you have the wires perpendicular to the field that you're applying, it's a little harder to rotate the moments. But those are for 100 nanometer diameter wires. And E, what's different about E, because you can see all these properties are changing, but E is the extreme one. Well, in the case of E, they're all sort of isotropic, and they're separated from each other by a lot of copper. They just don't really see each other. So these are more like isolated nanoparticles. But for those of you in bio, they're like nanoparticles that are already nice in a chain. So you can see the signal that they're giving, which is convenient for a lot of applications. And here we're just showing that they're pretty isotropic because the properties are the same no matter which way we measured them. Now if we go to 35 nanometers, these wires are no longer wide enough in diameter to support a vortex. So I said that backward. This is vortex switching. Thought Randy might say something if I mixed that up. I've had a long week, you know. Yeah, this is vortex switching. So we basically are getting a minimum at 0 and 180 because it's a lower energy state if the moments are lined up like this and they can rotate around like dominoes. You have a wall that travels through. It could be that all the moments are lined up and they curl around and switch together. We can't really tell the difference between those. But essentially there's probably a vortex wall moving through these. There's a lot of simulations of this. I know Cornelius Nailsch was doing some with Ricardo Hertel. Nice pictures of spins rotating, all the theory behind that. So you can see the vortex that propagates through. And that's what's harder to do at 90 degrees when the wires are perpendicular. So why are we not getting that behavior here? It's because the 35 nanometer diameter is too small to support that vortex core. Now this is not exactly coherent rotation either because it actually should look like this smooth sine wave, only have a maximum at 0, minimum at 90, and a maximum at 0. So what we think is we're just not getting the same mechanisms for all the different angles we're applying the field at. But at 90, we're pretty sure we're having coherent rotation because you apply the field this way, you force all those moments to come out in the direction they really don't want to go because the shape anisotropy is along the wire. So when you take the field away, well, the moments rotate where they want to be. Then you have to force them back down that way. So there's a minimum right at 90, and it's actually pretty interesting. This magnetostrictive alloy with 35 nanometers has a huge coercivity until right around 90. And otherwise, yeah, so it's just different. If I wanted a biological application to say, give me 3 different barcodes, I'd say, all right, we're going to make you 100 nanometer iron gallium, this isotropic iron gallium, and we're going to make you 35 nanometer iron gallium. And you'll be able to distinguish those magnetically from each other. So it's a nice diagnostic tool. All right, so read sensors seem like something I should focus on a little bit more, and then some cancer stuff, sort of half and half for the rest of the time here. So you've seen this a lot also. I don't have to say a lot. I think Mike Kotsky's words yesterday at Seagate were this is the driving force, right? Higher areal density. These are the mechanisms that involve read heads. So every time there's sort of flattening out of areal density and then a jump, things all of a sudden get better. We're kind of getting to a plateau again. So I'd like to think a new read sensor would help the jump, right? So maybe this is how to get that curve to start jumping back up again. This is what read sensors look like now, which is the image I'd had on the first page for a while. I'll have to put it back there. This is essentially a shield that was grown. That means the permalloy. I don't know if you remember the structure here, but the right sensor inside here, oh, I pointed at the media, sorry, I meant the reed. This is the reed sensor. That's the right pole, right? The field comes down and switches these bits up or down. It goes through the soft underlayer. It returns through a thick return pole. So the flux is focused here and then returns looser there. So you're switching here. But then the reed sensor's over here. The return pole is coupling, is acting as both a shield and a return pole. And you need another shield on this end. That ensures that your reed sensor is only detecting what's underneath it, not all the other bits. If you want a fun exercise, calculate the field coming off the adjacent bits of the one you're trying to measure. Within just a couple, you have a lot of field coming off all the other bits. Can't read the one underneath you. So they shield that out. Now here, so that's the shield that's being grown right there. It's just a film of, let's say, permalloy or something grown first. Then there's all the layers that are the sensor. So there's the synthetic antiferromagnetic. Then there's a tunnel junction. Well, this is actually a Heusler alloy. This particular example from Jeff Childress's paper. So I just stuck this in today when I remembered I wanted to show this for this class. But Jeff Childress wrote a paper in 2008 that had the smallest Heusler alloy sensor at the time, and this is what it looks like. So there's antiferromagnetic, ferromagnet, a layer like our copper, and then another ferromagnet, then a little layer before the shield. All right, so that's their structure. They've got all the layers. They have to pattern a bit, wipe away everything, coat it all with aluminum oxide, conveniently. Then they put down what's called a hard bias on either side. That ensures that their free layer is fixed in the direction they want until they're measuring bits. And then they chemomechanically polish all of that. So you saw the chemomechanical polishers yesterday. Then they put down the shield on top. All right, so let me just give an example, the hard bias. If it's perpendicular recording like this, your fixed layer is pointing down. Your free layer, because your stack, although they grow it like you see there, right? You grow the different layers, adjacent, copper, 2 ferromagnets. You actually do your reading in this direction. So now the media is flying down below this, and my free layer is able to switch. But I want the hard bias to hold my free layer in this direction. Then as I'm skimming over, or let's say the media is skimming under this head, if my free layer is drawn down, I get more resistance. If it's pushed up, I get less resistance because it's aligning with my fixed layer. But you need that exchange bias to kind of help that happen. All right, so that's for perpendicular media. But notice that they coat this whole thing in aluminum oxide. Then they put all that other stuff on it. Yes, of all the details to forget, probably plugging in my computer is not a good one. All right, so here's our idea for having nanowires as your reed sensors. We're going to put 3 in a row to start with, and they're already in aluminum oxide because we're going to grow them in that template. You don't need aluminum oxide to be the template. If you have some other favorite template from doing your bit pattern media and you want to fill that up, that would be fine too. We like the aluminum oxide because we know how to make it. But we'll do some layers like this, and that's about the right size for a reed head, and we'll see what kind of magnetoresistance, resistance, and so on it has. All right, so here's the first sweep, where we apply a current, and we see spin transfer torque switching. Now, for all the RAM talks that you hear, you want that switching current to be as low as possible, right? You want this to happen as low as possible, because you want to be able to switch your bit back and forth if it's RAM. But if it's a hard drive, you don't want the current switching your hard drive head. You want the media underneath to switch your hard drive head. So you want your switching current density in the case of a reed head to be very high to make sure you don't have current-induced noise in your head. The media is going to be switching only. All right, so here we get these types of measurements. We always get these jumps. They're at about these values. And we said, you know, what if we get these jumps because this smallest jump we ever see is 1 nanowire. So we're getting a certain number of nanowires, and our probe came down and it picked up another one. Then that jump would be, because we added a parallel resistor, another nanowire. Well, we worked out that this would be 13 nanowires. We had 15, 16, 18. And if you do that calculation, then you find that you're getting a resistivity of about 120 ohms. And our nanowire, which looks like this, is 190 nanometers. So, you know, that's kind of unsettling because that's about bulk resistivity. And most people that either measure or calculate resistance in copper, because most of it was copper and then there was a little tri-layer in the middle, would say, well, the mean free path of an electron is 40 nanometers. It's this length. That arrow's there because with respect to this diameter, that would be the mean free path of an electron. It's going to, as soon as you try to apply a voltage here and run a current through, it's going to be scattering off the sidewalls. You should get 10, probably even 1,000 times higher resistance in a nanowire that size compared to bulk. And we're not seeing that. So Nanoletters said, well, you know, oh, actually, wait, let me first say, we had all our nanowires. We're coming down with a probe. We pick up more, and we end up seeing different resistances. So we said, why don't we, when we get to this spot, adjust the pressure till we get the same, somewhere around 9, right? There's some noise, but you know you have the same number of nanowires when you're about 9 in all the different samples. So these curves were adjusted by normalizing them to the value of 13, but every single one of these curves was measured exactly as you see it here. No changes. Taking a little noise around 0. But that current switched at exactly the same spot. These currents switch at different currents because there actually were more wires there. We just adjusted the height so we could see what the loop looked like. So for sure, if you pick up the same number of nanowires every time, you're going to get the same switching current density. And we think it's a very high switching current density, which again we want for a read head. And we were pretty happy with that result. And Nanoletters said, well, we don't really believe you. We want a histogram. Well, they also want to reply in 2 weeks, so it took a while. And we finally ended up getting a histogram. All the purple measurements there were seen as measured, the very sharp tip coming down and measuring individual 10 nanometer diameter wires. So we said, you know, these look like they're probably single, because maybe you'd say those could be 2 single wires and these are double. But it's parallel resistances, you should get half, right? If you measure 1 wire, you get a value. You measure 2, you should get half that value. And we never see a measurement around 80 for all of the different measurements we took. We actually had more down under here that are not as significant. All right, so we said, okay, what if these are single? And these are just small wires because our areas have a Gaussian distribution. So if we have small wires, they'll be more resistive. Big wires will be less resistive. But it's not very Gaussian looking. Well, let's do some statistics. Every possible combination of these would give us this, which looks like what we thought were 2 wires. And every single possible combination of these would give us, 3 wires now, would give us this statistic, which looks like what we were pretty sure was a measurement of 3 wires. So statistically, it looks like we're hitting single wires, double, single. But why aren't we getting a Gaussian distribution? Does anybody know? You can make me feel dumb because it took me a little while to think about this. So when you're measuring resistance, it's resistivity times L divided by A, right? So we shouldn't get a Gaussian distribution. We should get an inverse Gaussian distribution when we're measuring resistance, which would give you a highly probable low value and a high value tail, kind of like we're seeing in our data. So Nanoletters said that was fine. They'd go ahead and accept that. And it went through a little more than that, I'll say, but eventually it is published now. You can find it. And you can speak to me about the details, but not in front of everybody. Anyway, so another problem that came up is we realized the ITRS Roadmap, it is the #1 challenge in the ITRS Roadmap. The #1 right now is the interconnects have too high resistance. They can't get that down. Things get hot. The RC time constants go up. So we are saying, you know, you need some vertical interconnects. You have to watch the sidewalls. And our sidewalls are very good. Maybe we're going to see aluminum oxide even just because you could fill your via and have sidewalls that are perfectly smooth. We'll see. But that was another thing that made it interesting. And here's where the read heads come in again. Here's our aluminum oxide, which would be the first thing you'd want to do if you were processing these as a read head. We can go ahead and let them pattern a 30 nanometer dot. If they try to pattern the layers that I showed you, the Heusler alloys, smaller than 30, then the sidewall damage is so bad they don't even get an MR. And that 31 had 5%. So our wires have 18% MR, magnetoresistance. And when you put a blob that's 30 nanometers on top of our structure and mill away everything around it, you're left with a 10 nanometer wire that's already in aluminum oxide. So the sidewall damage is happening out here where you don't care about it. Then you can put down your exchange bias, lift that off, put a shield on, and you have a sensor. 30 nanometer diameter gives you 10 nanometer structure already surrounded. And if you want to do something even easier, make a 100 nanometer blob by 30 nanometers, and you'll have 3 10 nanometer devices already in aluminum oxide, so an array of read heads ready to go. This is sort of explaining why you might want an array, and I'll skip over that. Here's the actual magnetoresistance of a single nanowire, 18-ish%. See, there's some noise there in the magnetoresistance. All right, comparison with other GMR. These are mostly Heusler alloys that we end up comparing to. And anyway, you can just see what matters is the area should be small, diameter small. The RA product should be small. That's a unit they go off a lot with these sensors. A TMR would have much higher resistance, so they're trying to go to all metal, so they have lower resistance in the read heads. We get about 30 ohm resistance in the actual stack itself. It's actually 19% MR, and these are actually, I guess, very high. Remember, you want a high switching current density for read head, and so all those parameters look like they could make pretty good read sensors. All right, I told you I'd do something really quick in RAM and then hop to the bio. So the quick in RAM is how we measure it, and basically that we can get a lot of different switching currents and that they're fairly low. So for RAM, you want a low switching current density because you want to switch between ones and zeros. And a simple way to do that we found is just take 10 nanometer for all your cobalts, vary how much copper they're separated by. If you separate your cobalts by just a little bit of copper, you'll see a certain switching behavior. Put a little more copper and so on. When you get to about 13 and 15, now at least you see bipolar behavior, which is pretty important. We want to be able to switch it with a low current and have it stay in the 1, and then switch it with a low current and have it stay in the 0. So using positive and negative current, we want to be able to store 1s and 0s. But the nice thing is, remember we have 10,000 time aspect ratio. We could grow this material, then that material, then that material, all in one nanowire and have 3 states in 1 bit, which would be very handy for high density. So why do we see this behavior? It basically comes down to the cobalt is the same, but it's separated by more and more copper. And what happens is, this is kind of a fancy way if you want to read the VSM curves. You see, we switch from having the easy axis parallel to the wire to perpendicular to the wire. And that's because when the layers are very close to each other, they kind of stack like refrigerator magnets would stack if you bring them together. But when they get further apart from each other, they tend to align this way, and the pancake shape takes over at that point. When you switch from your anisotropies, you also switch your switching current density at where that actually happens. And here we're just showing that we've calculated an effective field. If we look at any one of those layers, you say, why is it switching differently? We can take a look at all the magnetizations of the layers up the same wire and from separate wires, calculate the field they're applying on a single layer, and then this all makes sense. So, all right, so into the cancer, because I'm at the end here. We've put this thing in a microfluidic channel and detected flow, and here's the cancer part. I always like to have the puppies here because I'm normally running towards the end, and they're awfully darn cute. But they're also the veterinarian doctor that works with this guy. He's an alumni from our department. He has a kennel club, and his kennel club funds a veterinary doctor. And that was my link to get to meet somebody who had osteosarcoma cells. Literally an alumni sitting in this room listening to a quick survey of what the faculty are doing. And he said, hey, I know someone in the veterinary clinic. He works with my puppies, and he could get you osteosarcoma cells. So I'm just going to show you, we have a different mechanism. You already heard about hypothermia, which is nice. Our thoughts are, let's get these nanowires in the cells and rotate them with an external magnetic field and scramble the cells. All right, and that's what we're doing there. You kind of see the wires moving as we have a big magnet. We're just kind of dishing around out here. And then we have osteosarcoma cells. Mix them with some nanowires, let them incubate for a while, and then take a magnet and put it out here. And you can see which cells uptook a nanowire because they don't look like they had a nanowire, but they're rotating with a magnetic field, and the others, pardon me, are not. If we functionalize, we can get them to go around the nucleus, which is a handy place to be if you want to apply some hypothermia. And otherwise, we just want them in the cytoplasm. So what we have in a paper that just got published this spring is what we're calling self-dispersing nanowires. Because if we put RGD on our nanowires, RGD is a peptide that is on your extracellular matrix. Osteosarcoma loves to bond to the extracellular matrix and form a tumor that's stationed somewhere in your bone. So we think our wires look a lot like the extracellular matrix. We're going to put this peptide on. Now the osteosarcoma sees what looks like an extracellular matrix environment, and they bond to it. Once they're grabbing at our nanowires, because they're used to bonding to that, they internalize the nanowires. So they actually break up clusters for us if we happen to get clusters to form. Once those wires have been pulled off a cluster, they're inside a cell. When the cell divides, both daughter cells have nanowires, and the cells divide at a normal rate. This coating doesn't stop their normal division. It doesn't make them go crazy, so it's not toxic either. But here's 3 different lengths we use. We're showing that we can functionalize either the magnetic component or the ends, which are the gold, depending on what we put on the coating. And then this just hysteresis of them. We have shown that they don't cause cells to die very readily when they have the coating that we're interested in. We had to really load the sample before we see any cell death at all. And these are just other coatings, and this is kind of a classic silica that's compared with cell death. So they're not cytotoxic that we can tell. This is with white blood cells. They don't elicit an inflammatory response, which is a good first test of toxicity. And you can see bare nanowires do kind of limit the metabolic activity of the cells a little bit. PEG, which is a very common coating, it's called the stealth molecule. Stealth, because whatever particle's coated with PEG, the cells kind of don't see it. It's just a big waxy molecule. And sure enough, the cells kind of don't really care how much you've put in when you put in PEG. But when you put in RGD, they have that normal metabolic activity that you'd expect of the cells. So here's a movie of what they look like mixed in with the cells. You can see the clusters kind of dividing up. They get all the initial clusters you see sort of get broken up in little pieces. There's still a couple big clusters. These cells are adherent. So to divide, they have to come up off the substrate, divide, and splat back down. So by that time, I normally point at that one, and there's one down here that's about to go. It'll come up off the substrate like that, divide in 2, and go back down. There's one that went. Those are all just normal behaviors. It happens the same whether or not there's nanowires there. And every single daughter cell is taking up nanowires. So by the end of a normal period of time, let's say 24 hours, most of your population ends up with a nanowire in every cell because they're breaking up the clusters, dividing, and adhering. Every new cell that runs into a nanowire adheres to it. When it divides, it continues splitting, and we end up with a lot of nanowires dispersed throughout our cell population. I'm not going to go into all of these. They're the details of what I just told you. I brought this right here. It's a stir plate, and I think I have 3 slides left. If I put a beaker here and drop a stir bar in there, then I can turn this knob, right? And there's a magnet in there that's going to rotate, and you'll see a stirring. If I have a beaker of nanowires, and I put them on this stir plate, and then I drop in a stir bar, they all stick to the stir bar, so it's not very entertaining. But if I just put them on the plate like this, and I cause it to rotate, we tried to find out a way I could zoom up on this. Can the people in the front row see it blinking at all? And I can try and put the laser on it. Sometimes helps. Can you see a kind of a rotating motion? So that's the nanowires spinning around in there. And if I were to have an assistant from the audience, which I honestly don't think I have time for, I could speed it up and you'd watch it go faster and slow it down, and it would slow down. Because the nanowires are just responding to a magnetic field. It's like so simple. We used to just do it as a trick for the program managers. So they'd give us more money. And then we realized we could use this too, you know. All right, so that's what you're seeing in this movie is there's some vials with nanowires and they're spinning, and I've got a laser pointing through there. So let's go to the next movie, which is more interesting. This is actually 2 glass slides that have a UV curing polymer. So actually they're quartz slides. With UV curing polymer, we're shining the laser through, and we have it on a stir plate like this. And then we shine the UV light on. As the polymer cures, when you hit the gel point, the wires can't spin anymore. They're kind of stuck in there, and they kind of respond to the magnetic field, but they don't spin. And when you allow it to cure enough that it turns glassy, they don't move at all anymore. And it's convenient that right at that point where they go from spinning, those are the same shear modulus that people measure for cancer cells. And when the wires go to just kind of a rocking, they can't spin anymore, that's the shear modulus that's measured in healthy cells for epithelial cells in the bladder. And there's a lot of other examples of, there are some cancer cells that you think of as harder because a tumor is often detected because it's hard, but the mesenchymal cells on the surface that form dendrites, that metastasize, they're actually squishier than your normal healthy cell or than the rest of the tumor. And those are the ones we're hoping we can kill. Let them pick up some nanowires, spin them, and then maybe even be able to get a magnet in there and extract our wires before they go anywhere else in the body. So it kind of depends on where the tumors are. We've obviously, as we talked about in the last discussion, just been having fun with this, but there is clearly an application here. And as I mentioned, we have a lot of other results lately with a lot of different techniques that are just getting more and more interesting. So with that, let me leave this up here, and of course my acknowledgments of funding I should have IEEE on here because they've given me travel money. But since I'm in Minneapolis and I didn't go very far, I won't worry about it. All right, thank you very much. That would be